Hello everyone, welcome back to machine learning. In this video, we are going to look at an example of decision trees using Scikit Learn. Now, Scikit Learn is a package in Python, and it allows us to use machine learning models on real-world data sets. So here we are going to look at the decision tree model using Scikit Learn. And I've built this notebook in Jupyter Notebooks, which is what I use to write Python code. And as you can see that it definitely is not too complex, as we have in step 3 itself fitting a decision tree classifier. So it does not require you to have an extensive knowledge of Python, though some knowledge of Python always helps when we're loading the data, analyzing the data, looking for which features to keep, which to reject, and so on and so forth. But in general, this is a very easy toolkit to use and ramp up once you have some basics of Python and some basics of the toolkit itself. So let's look at an example so it's helpful, and hopefully this would become clear. We use pandas for loading the data set and storing it, and that is another thing that I always recommend, because that definitely gives us a very good data structure to store the data and to crunch the data whenever we need. And sklearn is what is used to refer to Scikit Learn. And we are going to be looking at the iris dataset. So the iris is a flower dataset which has different features corresponding to different kinds of flowers. And there are 3 classes here: the Centosa, Virginica, and I think Versicolor. These are the 3 different kinds of flowers that are in the iris dataset, and there are different features that specify their sepal length, petal length, and so on. So these features are what we are going to use to predict which class of flower this particular data point is from. So this is the data that we are using, and then we are going to use the decision tree classifier. So we import that, and now the first step, we are going to load the data and store it into a pandas data frame object. And the code for that is here, where we load iris into a variable called iris, and we split the data into features and target. Like in any other machine learning model, we need features. So this is a classification problem, right? So we are going to use the features to predict a target. So remember, we have usually data looking like this, right? Let's say this is data instance 1, and then we have multiple columns. Let's say feature 1 through feature n, and then a target or y. So this node, this value here is the target, and this is one data instance. So what we are essentially doing in x and y is that we are separating these. The x's are all the features, so those go into x. Now it's a capital X here because x is a vector, right? It is the feature vector here for each data instance, and for all the data instances together, it will be looking like a table. I'm just going to overlap here and then I'll erase it. So data instance 2, 3, so on, right? And then this entire table is going to go into x. So x is a vector for each data instance, and for all the instances together, it is this entire table here, this entire thing. So that is x. and the corresponding y's of all these data instances are going to go into the sky. So for each data instance, for one instance, y is a scalar, right? Because you have only one value of y. But you are having all these y's go into this data structure here. So we have just split the data into two parts, where this all thing is x and this whole thing goes to y, right? So that's what is happening in loading the data and storing it into a pandas data frame object. Now, the next step is to fit a decision tree classifier. Now you can see how easy it is. We are just going to invoke the built-in decision tree classifier and apply it on the data set that we have just loaded. I'm just going to erase these things just to make some room. All right. Now, fitting a decision tree classifier. So we are fitting the decision tree classifier with a max depth of 2. So we are specifying a classifier with all the parameters that we need. We'll see that there are a lot of parameters, so we are just specifying the maximum depth for now. And then the fit classifier, after the data has been fit, now it is stored in tree. So we have tree, which first specifies the kind of classifier, and then we fit the classifier to our data x, y. So we are using the entire data in x and the corresponding y to train our decision tree classifier. That's what it means by fitting the classifier. We are training the classifier on this data, and now tree, this contains the trained or built decision tree classifier. Now you can see that the output of this has many different things, not just the maximum depth. So the maximum depth is something that we specified. There is also something called the criterion, max features, max leaf nodes, so on and so forth. So these are specified to have build a specific kind of tree. So these are the parameters that are going to give us the tree that we want. Ideally, we have some notions about what we would like to see in the classifier, right? So here max depth specifies that we don't want a classifier that's too complex, too hard to read. And that's why we have put a limit on the depth. So now when we put a limit on the depth, let's actually look at what classifier we got here. So to do that, I will be using the GraphViz package. So the GraphViz package is a very, very good way to visualize the tree that we just built. Now, decision trees are known for their interpretability, in the sense that when you look at a decision tree, you know how the decision-making process is flowing. And we have seen that in other examples that we have worked out in the past videos. So we know that if I want to play tennis or not, if we want to decide whether to play tennis or not, I'm going to use that decision tree, and I'm just going to traverse it, and based on all the information I have, and that should lead me to the right decision, which means it should be easy to read and easy to interpretable for a human person. And that is one of the very good things about decision trees, and which is why people really like them. It's still hot. People use them in various different ways, such as in random forests. The component is a decision tree, and also it has a revival in terms of how models in machine learning can be made more interpretable, and a crucial model that is discussed there is the decision tree. So, all right, long story short, I'm going to now go and show you what is the tree that we just built. And I'll have more details on how to do the graph viz in the description, and I'll share some notes on that, where you can actually use this package to store your decision tree. All right, so the first decision tree is this one. So this is what we built, and the max depth is 2. Let's see here, that's right. This is depth equal to 1, and this is depth equal to 2, right? And now, not just is this visualization giving us the attributes that were used to split, it's also giving us some other things that are very, very useful for us, and especially when we are tweaking in the process of building the tree and getting the tree right, these are going to be very, very valuable. So for example, here the first attribute that has been used to split the tree is petal length less than or equal to 2.45. So we have a continuous valued attribute, petal length, and we are splitting petal length at 2.45, and anything that is less than or equal to 2.45, if it is true, it is going to traverse all the samples that have petal length less than or equal to 2.45 are going to go in this path. And what about petal length greater than 2.45? Those are all going to go in the false route. They're going to go in this path in the tree, right? Now, let's look at other things that are there in this box. The first one is Gini. Now, Gini is a measure that is used to split, to find a node to split on. It is very similar to information gain. Now, proceeding to the next information that is given on the node, samples equal to 150. So now this refers to the number of samples that are entering this node, that are coming into this node before the split. So number of samples, data instances that have been input to this node before the split. Now the next piece of information that we have is value, where we have the split of the data instances according to their class. So now we have 50 in Setosa, 50 in Versicolor, and 50 in Virginica. So there are 3 classes in our data, and the first class value is Setosa. The second one is Versicolor, and the third one is Virginica. Right, so there are 3 different values, and then for each of these target class values, there are 50 samples. That is what is indicated by this piece of information here. Now, we have another last piece of information here, where the class is given as Setosa. Now, this is what the decision tree would predict if there were only this particular node in the tree, which means if the tree building stopped here, like only this node is there, the rest are all not there. If that is the case, then this node will return the prediction Setosa. And that it has come to that by looking at these values. Now there are 50 each of Setosa, versicolor and virginica. There isn't even one which is highest. So it is just picking the first one, Setosa, and it is going to return that. So that's what is happening here, where it says class equal to Setosa, right? And we'll see as we go further, the class will change, and we'll see it corresponds to the most occurring class within this list. And now this is relevant because remember, we did not build the tree to the maximum possible depth. We cut the depth at 2. So we specified the maximum depth to be 2. So we only let the tree build to a particular extent. So we are not, maybe we won't, or maybe we will have a pure leaf node. But what happens if we don't have a pure leaf node? Still, the tree has to make a prediction when it reaches a leaf node, right? So that is why this particular thing becomes relevant. So, and we can see that this is predicting a class at each and every node, even if it is not a leaf node, which is just for information, and we can use this information when we are debugging the tree. But as you know, that this prediction class right here is not actually relevant because the tree is continuing to build and this is not a leaf node. So only relevant when this is the only node in the tree, when this has to, or this is a leaf node where it has to return a prediction. I hope that makes sense. So now let's actually go down on the left. Now we are traversing the true branch where we have the petal length less than or equal to 2.45. And here, when we go down, we see that pretty much this classification has made one class pure. So when we have a petal length less than or equal to 2.45, all the samples in the true branch are in class Setosa. So that we can now read pretty easily based on what we have already learned using the root node. Now we know the Gini is just like information gain. It is a measure. So closer to 0 means there is less and less impurity. 0 means there is no impurity. And this is true for here because all the samples that are coming through this, there are 50 samples that are coming in this branch, all are in the same class, right? So there is 0 in the other classes, and that class name is nothing but Setosa. So which means that now with this one split, we have one pure class, and we are going to use that here and predict Setosa in this branch. Now let's go to the other branch, now where petal length is greater than 2.45, and now we are saying that we are going to have to split it more because it is not pure. So we are going to use Gini again, and we are going to calculate Gini, and we are going to pick the best attribute based on Gini. So this is just like information gain where you use that measure and you pick the best attribute that is coming out of that measure. So now we have petal width as our next best attribute to split on, and we have 100 coming into this node. So this 100 is coming into this node, and we have 50 of them in versicolor, 50 of them in virginica, and which is why the Gini is at 0.5, right? So this is another way to read these scores without really calculating them. I always like intuition when we are constructing the decision tree. We want to be able to look at the score and see which way it is tilting, rather than just resort to full length calculations for the exact number. These scores can give us a very good idea of how our data is looking like, and if we have to split again, and so on and so forth. So now coming into this 50 in versicolor and 50 in virginica, right? And Now we have chosen petal width less than or equal to 1.75 as our new attribute to split on. Now this is going further. Now this is the true branch and this is the false branch. So traversing this true branch, now we get samples 54 into the true branch, which means we are getting 49 from versicolor and 5 from virginica are coming into this branch. So these examples, these data samples, right, have, or 54 have petal width less than or equal to 1.75. Now, this is not pure yet, but we have restricted the depth to 2 by default. Because we have hit that depth, this becomes a leaf node. And because we are not building the tree beyond this point, anything before 2, if it is pure or at maximum depth of 2, will become a leaf node. So now this node here, right here, now this is a leaf node. So all colored nodes are leaf nodes. Now we have versicolor and virginica, and we can see that versicolor is way more, contributing way more in the number of samples than virginica. So based on which the prediction would be versicolor. So if we were to traverse this path reaching to the green node, our prediction would be versicolor. Now let's take the other branch. In the other branch, we can see that because we had a total of 100 samples and 54 came here, 46 will go to the other branch. Now in 46, we can see 45 are in virginica and 1 is in versicolor. Now based on this, we declare the class to be virginica at this leaf node. So both of these are leaf nodes, and they are at maximum depth too. Now we can see that though it's not a perfect classification, we can see that there are only very few exceptions to what we have reached. So if we were to split again, then we have to worry about these, right? These 5, because these 5 are virginica, and this one right here, which is in versicolor. So these are the things that have been misclassified, and these are the ones, if we were to split the tree more and more to greater depths, these are the ones that we will focus on to get them right. And like always, splitting the tree to really reach a perfect classification at training time may not be helpful at test time. So this is why we have pruning. This is why we don't build a tree beyond a certain point. We only build a tree till the point it is able to generalize, read better, work better on test data. So remember that when you're constructing the tree. So let's go back now to the document. Now we have fit a tree of maximum depth equal to 2, and then we also have visualized the tree. Now let's see what happens when we fit a decision tree classifier without defining maximum depth. So now we do the same thing. We fit the tree, but we don't specify a maximum depth. That's why the maximum depth is none. Now we export to GraphViz again, and then we have another file for us to look at. So let's now look at that file and see what happens and how it looks. Now I believe this is that file. Now, as you see here, so we actually had stopped it here, right, for maximum depth equal to 2. Now, all these things make the tree much, much harder to read. Now, if you were to decide based on what is here, now that would be much simpler, but still effective, because there are only very few ones that are not really in the right class when we are predicting, right? But when you are splitting it again and again, now it makes the tree much more complicated for getting a perfect classification. So here, if you see and go all the way down to the leaf nodes, so I'm just going to mark all the leaf nodes here so we understand. Now this is a leaf node, 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 this and this as well, right? So all these are our leaf nodes, and if you see, most of these leaf nodes are actually classifying very few number of instances. For example, so this is a good leaf node, and this is all coming out of this leftmost branch, so this. So from 49 for versicolor, we made it 47, which is not like a huge improvement, but we made it purer. So this is the leaf node that we get. So this is in fact very similar, this classification, the ratio between 47 and 0 is very similar to what we had for 49 and 5. Not too much has changed. So this is one pure leaf node that we created after 2 more splits, and still has quite a number of instances getting classified here. So here, let's mark it down. This is 47. And there's another one which is also kind of useful, which is the rightmost one again. So rightmost one is for Virginica, where we have from 45 it went to 43, like 2 instances, which were used for multiple other splits, and this became pure, right? This is 43. Now we have way few number of instances in all the other leaf nodes, which means the entire path of the tree was built for classifying just that one instance or 2 or 3 instances, which is a complete waste of the tree. So this is another way to understand when you have to stop building the tree, when you are splitting to the point that there are very few number of instances when compared to the initial number of instances that you're classifying as part of that leaf node, then it's not worth the split. So for example, we have 150 data samples here in total, but this particular path here has way few instances. In fact, it has only 1. So this entire path, so I'm just going to mark the path in, let's see, blue. Okay, so 1, 2, 3, 4, right? So this entire path was built for 1 instance, and that's way too much effort for way little gain. And that will not actually scale at test time, because this could have been an error in recording that data. It could have been a data which is just an outlier in the data set and may not be present in the test data. So this kind of these specific branches don't generalize well on test data. Let's see here. So if we continue, we have 3 instances in this leaf node. We have 2 in this leaf node. We have 1 in this leaf node. We have 1 again here, and this is 2. So all these are classifying way too few instances for them to be beneficial, and they are not really contributing much to your decision tree, which means that stopping it sooner is helpful. And in fact, for this particular data set, stopping it at depth 2, I think is ideal, because after depth 2, we can see that it's really struggling and not really classifying too many. So even at depth 3, right? So this is built for 6 instances, which is still a small number when compared to 150. And this is for 3 instances, again, not a big number. So I would say that just by visual examination and not really looking at any test data, I would say that stopping at depth 2 along this line here is probably a better choice. So a lot of these visual cues would help you to understand when to grow, when to stop growing a tree, and that those kind of insights really help in performance. And I cannot emphasize this again and again. You cannot expect a model to just run it and just work on any data set. So that never happens. You always have to understand where the model is failing, how to make it better, understand what kind of features it's using, how it's using them. All these things are necessary for you to make a model work on any data set. And decision trees are no exception, but decision trees are in fact much better in my opinion, because you can look at the tree and you can have lots of these things figured out, so you can build the best possible, most interpretable and generalizable tree that you can build. All right, so now let's go back to our document. So here we have the next segment here, where we are going to see how we can make a prediction on a new data sample. Now, to make a prediction, you will get the values that are for the new data training, new test instance, which are for the different features that are there. So here we have sepal length, sepal width, petal length, petal width, I think, and we have these values. And now when you have these values, what you typically do, you do what you do in other decision trees, how we did in the example that we worked out. You pass these in the tree. So you use the value and compare to the value that is used for the split, and then you traverse the path accordingly. And then when you keep doing that, you will get a prediction, and that is the prediction that we output. So this part is pretty simple. Once the tree is built, you can use this, and when you have multiple examples, you run this for all the examples, and then you see which ones it did not predict correctly, which ones it predicted correctly, and then you calculate performance measures such as accuracy, precision, recall, and you output them. Okay, now I'm going to go into a couple of things here that are easy to customize and that would be helpful for you to try. The first thing is, of course, the criterion. Now, the criterion is the main thing that we use to split the tree. So information gain is a criterion. Variance impurity that we looked at in the homework is a criterion. And this one, Gini index, is another criterion. So I'll do another video separately on the Gini index, comparing that to information gain. Look out for that. It's not there yet, but these are all criterions. These are all measures that are used to split. And by default, the Decision Tree Classifier and Scikit Learn uses Gini. And you can use information gain. It uses entropy in the calculation. The information gain is called entropy in the Decision Tree Classifier. So you can use the same thing that we saw in class by changing the criterion to entropy. So if you don't say anything, it will by default pick Gini index. Splitter. So splitter is always best by default. Best is split on the best value. So that's what we saw in class and also here, right? So it's split on the attribute which has the best value for Gini index or information gain. Now, what does random do? So it's interesting what random does. It also does the best because that's what makes sense, right? So you want to pick the attribute which has the best value for your measure, and that is the one that you want to choose. But random splits the features into a random subset. And then in the random subset, it will pick the best feature, the feature that has the best value for your measure of splitting. Now, how is this helpful? This is helpful because sometimes you want to experiment around with features. You don't know which features are helpful, which are not helpful, especially in data sets where there are a number of features. It's not really useful for example, the iris dataset where you have just 4 features. It's not really useful, but sometimes you can incorporate some random feature selection by just including this, and that could restrict the number of features that the decision tree looks at for picking its the next attribute to split on. Now, this is helpful in many different ways. First, a little bit of randomization always helps in making a model generalizable at test time. And another way it could potentially help is that if you have random set of features, you are restricting the total number of features, right? And this would also mean that the decision tree has fewer choices to split, and therefore the finally built decision tree is not too big because there are fewer choices for your decision tree to look at, to select for your feature split. So for example, just to make things clear, best would select the best in the entire feature set. So it will look at the entire feature set. Whereas random will look at a subset of features. Subset of random subset of features. And in that, it will select the best. So best in a subset, which means that maybe the best was in the feature that was left out. So which means it will add some different paths to your decision tree. So normally random is used to make models explore a little bit. So if you don't select the best and select the second best, what happens? Maybe you build a slightly different decision tree, but maybe that decision tree is helpful to you at test time. So you want to let your model explore a little bit and find out what are some other maybe less than optimal paths on the training data set, but that could be great paths and great models for the test set. So you want some amount of randomization, some amount of exploration that the model could do, and that is achieved by using this random. And if you were to use random, what I would recommend is that you use random, run it a few times and build different trees and see how that actually looks. Maybe they look entirely different. Maybe they don't look too different. And then you can see which one of them works best on the test data set. Or what you could also do is that you could have 5 different versions of the decision tree built using random and then run all the 5 on the test and then report like an average. So that also helps, so that some models which have too much of error on one side, you can compensate by having some amount of randomization built into the model. So that's why this helps. And as we get it further and further into the class, you will understand what I mean by exploration and how that could help models achieve a more optimal state. All right, and then the maximum depth. So this is something we used, and this is again to prevent overfitting. And we saw that a overfit decision tree, like a tree without the maximum depth, can not be that interpretable and may not be even that useful and may not perform that well on the test data set. Right, and then there are other ones which you can actually look at, and another one that I would recommend looking at is the min impurity split. So again, if there isn't too much difference in the impurity, then maybe we don't want a split. So if you are considering splitting by an attribute, using an attribute, but the impurity is not too different, so that is something you can regulate by using min impurity split. So if the impurity is going to remain the same after the split as well, then what's the point of splitting? So impurity is, let's say, 50 versicolor and 50 virginica. And then after the split as well, it is going to be very close, let's say 49 versicolor and then 51 virginica. So that's not really too much of a deviation from the data that is coming in, and you don't really think that's a good split. So that's why we wouldn't recommend splitting there, and then we can set that as a regulation using min impurity split. All right, so now I have the same classifier, decision tree classifier built here with the criterion to be entropy, and the max depth is equal to 2. So I just want you to look to show you this one as well, because this is the one that we learned in class. Entropy, nothing but information gain in this classifier. And let's see what happens. Right. So now we can see that when we use information gain, we have a pretty different classification. In fact, this is very different from what we saw for Gini index. So let's actually see its petal width here. The first one is petal length here. So this is petal length. The root is petal length, but the root here is petal width. So it's entirely different. I just wanted to tell you that it could be very different. And so these measures can give you different trees, and sometimes some measures work better on some data sets. And this is another thing to experiment on when you're building the decision tree. Don't take it for granted that some measures are always good. It's not really true. Some are way better than the others. So for example, if you see here, for depth 2, I just want to make another point here. So let's actually traverse this tree and see how the classification looks. For example, if you remember, for the other one, the Gini index, we had almost near perfect classification at depth 2, and we were actually arguing that depth 2 in fact is pretty good, and we shouldn't want to split the tree further because it gave us a very good classification at depth 2, right? So that's what I remember. So now let's look at entropy or information gain, and we'll see how the classification looks. So let's look at the right side first, because this looks like a perfect classification and already a leaf node on the right. So the right one looks good, where we have 17 in virginica, and the rest are 0, so it's perfect. Now let's go to the left. So the left here in this path, we have all 3 classes, and the setosa and versicolor are near 50, because the only thing that actually went to the right is virginica. So only we have the other 33 here. Now what happens when we split again based on sepal length? So when based on sepal length, when we split, we have again a really confused classification here at depth 2, where we have all 3 classes, setosa, versicolor, and virginica on the left, and on the right again we have virginica and versicolor. So we have less than ideal classification at depth 2, I would say, because here 8 and 12 are very much comparable, and we're still going to predict virginica, but it's not really that much of a difference, and it's not clearly Virginica, I would say. And this one is far from pure, this node, the left node. So this is again true, this is false. So the right node is not pure. Virginica is a majority, but not clearly a majority here, but there are 8 from versicolor. On the left, it's worse because it has all 3 classes and significant number of all 3 classes, 50 from Setosa, 42 from versicolor, and 21 from Virginica. All are pretty populous in the sample space, and it's not really clear why we should predict Setosa, though because it is the highest, it is going to predict Setosa, but I don't think it's looking right. So at depth 2, Ginny was way better than information gain on the iris dataset. But it's not always that Ginny is better than information gain as well, so that's why we need to play around with these parameters. All right, I'll see you again in another programming video. I hope you try these examples and also try them on other data sets and let me know how that goes. Thank you.